everyone, and welcome to the last lesson of Activity 23. Today's lesson is covering 23-3, and we're going to look a little bit more into using identities to solve equations as well as verify, which is where we're going to start on page 314. We're going to verify the identity. Now, this one's actually worked out in the book for you to start, but when we're verifying, reminder, one part of this is already going to be our goal, right? We want our goal here. So notice we have the sum of sine formula. So we would have the sine of theta times the cosine of 180, and then plus the cosine of theta times the sine of 180, which sine of theta is not going to be able to simplify, but cosine of 180 is -1. Cosine theta won't simplify, and sine of 180 is 0, so these cancel, and we're just left with that negative sine theta, right? So with verifying, you're just trying to make one piece equal the next piece in this. Now, looking at the examples below then for part A, again, we have a cosine sum, and our goal is to get this side here then. So we're going to plug into the cosine formula. So we have like cosine alpha times cosine beta minus sine alpha sine beta. And again, in this case, our alpha and our beta are going to be x and pi over 2. So again, we're just plugging into our formulas there. And then cosine of x cannot be simplified, but cosine at pi over 2 is 0. And then sine of x can't be simplified. Sine at pi over 2 is 1. Anything times 0 is 0. And we're left with that negative sine x. Okay. In letter B, we have a double angle formula that we're going to plug in for. So it's a switch up from the sum and difference. We have the double angle. So we know that sine of 2x or 2 theta is 2 sine x cosine x, all divided by the tangent of x. And if we rewrite tangent as the sine over the cosine, and if we multiply then by the reciprocal, flip, skip, and multiply, right? We end up actually being able to cancel that out. So it's just sine in the denominator, which will cancel with the sine, in the numerator. And then we get 2 times cosine squared x left over, which was our goal for the verification. Okay. Last example is actually looking at this as a difference of 2 squares, right? Because officially cosine to the 4th is cosine squared, and sine to the 4th is sine squared. So the difference of 2 squares, reminder, we can factor to be one is a positive, one is a negative, right? They're kind of, I think, conjugates here. In a way. So now we know that cosine squared plus sine squared is just 1. And then if you're multiplying that by cosine squared theta minus sine squared theta, well, we know that this is one of the ways we can write our double angle formula for cosine. So again, checks out that we get that answer there for verification. Okay. Now, the next piece then is now using these double angle identities usually, or obviously then officially we talked about half angle and sum and difference, but they tend to be the double angle identities to be able to plug in to be able to solve our equations. So before we only talked about sine squared and plugging in 1 minus cosine squared, for instance. Now we can use sine of 2 theta. So they're plugging in 2 sine x cosine x, or sine theta cosine theta, taking out the greatest common factor. We have a GCF here, and then setting each piece equal to 0 and finding our solutions where those values are happening. Okay. So a reminder, cosine of 2 theta officially has 3 different options we could use, okay? Now in this one, I would recommend you transforming cosine of 2 theta to use just the sine squared, because that's what our other piece is written inside. If that had been a cosine, we probably would have wanted to use 2 cosine squared x. So what we're going to do, though, like I said, is we're going to take this piece and make the substitution in that we have 1 minus 2 sine squared theta minus that sine theta equals 0. And I'm going to bring everything over to the right-hand side to keep my squared term positive, because I like to keep that positive, because chances are right now when I add that over to the other side, I'm going to need to factor. So everything is getting moved. This is getting moved now. It's positive sine theta. We're going to subtract the 1 over. So now this turns into a factoring situation, right? What multiplies to be 2 times negative 1 and adds to be 1. Well, positive 2 and negative 1 multiply to be negative 2, but add to be 1. So we could break this up so that we have plus 2x minus 1x minus 1, and our factors become a GCF of 2x here, x plus 1. A negative 1 can be pulled out, and we have x plus 1, so that we end up with 2x minus 1 and x plus 1, which mean our signs, we're looking at where does 2 sine x, or sine theta, I guess we should say, equal 0, and where does 1 sine x plus 1 equal 0. Oops, we'll say theta. So where does sine of theta equal 1? Half. And where does sine of theta equal negative 1? Okay, so that would be 30 degrees, 150 degrees, and 270 degrees for where it's negative 1. Now on this next one, I would recommend using the 2 theta that has 2 cosine squared theta minus 1, since we already had a cosine squared here to make our lives easier, because now we can bring all the cosine squareds to one side. So subtract that cosine squared from the 2 cosine squareds we already have, and we end up with 1 cosine squared minus 1. So where does cosine squared equal positive 1? Well, when we square root both sides, we end up getting where does cosine of theta equal positive or negative 1. Okay, so that's going to be 2 places, 0 degrees and 180 degrees over our interval from 0 to 360. Now, this last piece of information then is asking us, so far we've always been solving angles that inside here, these were always 1x, right? Or now we can make that transformation with the 2 thetas. We have some formulas, but what happens when there's numbers other than 2x or 2 theta? That's when these multiple angles are going to come into play. So this should be kind of the new information for today. So normally our interval, at least the one they're giving us, is 0 to 2 pi. When you have a multiple angle here, you are going to multiply this original interval by that value. So in this case, 3. So now we're actually going to extend this out to be 0 to 6 pi. So we're going to have more answers than normal. So where does sine of x equal 1/2? Well, we know pi over 6 and 5 pi over 6, but we're also going to have to find some coterminal values. So the coterminals to pi over 6 would be 13 pi over 6 and 25 pi over 6. Coterminal values adding to 2 pi here, 5 pi over 6, 17 pi over 6, 29 pi over 6. Those are all equal to 3x. So the last step here is going to be to take those 6 answers from 0 to 6 pi and divide them by 3 so that they all actually now become a denominator of 18. Since when we divide by 3, it would be a denominator of 18. Numerators stay the same. Okay, so let's try a couple more of these, okay? So in this first example for part A, notice we have a 4x inside here, which really means that our new interval is 0 to 8 pi, not 2 pi. Okay, so all the way to 8 pi. So we know normally tangent equals 1 at 2 locations, right? At pi over 4 and 5 pi over 4 in quadrant 3. And normally we'd be done, right? But we now need to keep going over our interval. So we need the coterminal value. So we'd add 2 pi, or I'm just going to add pi. So it would be 9 pi over 4 plus another 2 pi, because now this is going to be between 0 and 6 pi, and 8 pi, right? Because this would be our coterminal value between 2 pi and 4 pi, 4 pi and 6 pi, and then 6 pi and 8 pi, right? We're continually running around this circle to get all those values all the way to 8 pi, okay? So we would have all those values. And then we also need the coterminal values for 5 pi over 4, right? So that's going to be between 2 pi and 4 pi, 13 pi over 4, and then 21 pi over 4, and then finally 29 pi over 4. Because again, we have to consider all the way till 8 pi, so we have to kind of, consider 4 more regions. So if we list all of those out, we end up with 5 pi over 4, 9 pi over 4, 13 pi over 4, 17 pi over 4, 21 pi over 4, 25 pi over 4, and 29 pi over 4. Okay. The last step, though, is to divide all of these by 4. So think about when you're dividing by 4, really that's like taking your denominator with 1/4 divided by 4. Really what's happening is we're forming the denominator to be 16, right? Because you're dividing it and multiply the denominator. So your final answers would be all of these values just with a denominator of 16. Oops, and that again is your final answer. X equals all 8 of these answers. Now the next one, notice, is going to be a little bit less of a region to look into, and that's because this is only a 2x. So really our interval this time is going to be 0 to 4 pi, because we have to take the original and multiply it by 2. Okay, so a little less to work with this time. Now when we isolate sine squared of 2x, we had to add the 3, divide by 4, and when we square root, we end up with 2x, sine 2x equals plus or minus the square root of 3 over the square root of 4, which is 2. Okay, so normally from 0 to 2 pi, our answer would be all the family members here of pi over 3, right? So normally it would be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3, because that would be 0 to 2 pi. But now we also need to go one more quadrant beyond, right? Because we need to go not only from 0 to 2 pi, but one more to get to 4 pi. And so we would have to add 2 pi to each of these values, okay? So our next values then, we would also have to include 7 pi over 3. We would include 8 pi over 3, 10 pi over 3, and finally, if we add 2 pi to 5 pi over 3, we get 11 pi over 3. Now our final piece again with these is to make sure we divide the denominator by this value. So if you divide each of these by, divide the whole thing by 2, it means the same thing as multiplying by that number in your denominator. So these all actually will become 6s. So all of these are our final answer. Okay, all 2, 4, 6, 8 of them. Okay, last but not least, let's do a little bit of transforming here to begin with, because really what's happening is, again, we're going to switch our value, because instead of being 0 to 2 pi, we're going to go 0 to 6 pi, since we have 3x in here. And then notice, though, 2 sine cosine is very familiar to our double angle formula for sine. So we could say sine of 2 times 3x, right? The double angle formula for this one, okay, equals 0. So basically we're saying, where does 6x equal 0, since we transformed that? Well, excuse me, equals 0. Where does sine equal 0? And again, this is going to now be 6x since we combined. Well, sine equals 0 at 0 and pi. And then we also need the coterminal values. So 2 pi and 3 pi. And then all the way to 6 pi would make it 4 pi and 5 pi. And not including 6 pi. We'll divide all these answers by 6 to get x by itself. This is still 0. Now we have pi over 6. 2 pi over 6 actually is going to become pi over 3, since that reduces. 3 pi over 6 is going to reduce also to become just pi over 2. And then we have 4 pi over 6, which is going to become 2 pi over 3. And finally, 5 pi over 6, which doesn't reduce at all. So these 1, 2, 3, 4, 5, 6 answers become your final answer. Okay? And that's how you would do the multiple angles. All right, congrats on making it all the way through 23.3, and we will keep working with these in class.